For more than 100 years, one test has proven to be a tremendously enduring biomarker of acute illness, and that is the measurement of the pH of arterial blood. This is a tutorial that starts the course on acid-base balance, and I'm principally going to be talking about that test, the pH, or the hydrogen ion activity. A lot of people think they understand acid-base balance, but if you start digging down below the surface, they really don't understand much about it. And I'm hoping to unpack and unpeel some of the problems that people have understanding this difficult topic, although not quite as difficult as most people make it appear. So this first tutorial is about the hydrogen ion, why it's important, how we measure it, and what you really need to understand about the hydrogen ion activity and the pH. The power of hydrogen. This is the first tutorial in the acid-base series, and in this tutorial I'm going to discuss initially the physical chemistry of water and why that's important, hydrogen ions and the pH scale, water acids and water bases, and finally acidosis and alkalosis. At the onset, I want to make a couple of points. The body goes to considerable trouble to maintain its internal milieu. This is also known as homeostasis. A major component of this is maintaining the slight alkalinity of extracellular fluid and the chemical neutrality of intracellular fluid. This happens despite the astonishingly small quantity of hydrogen ion equivalents in both locations. I want to ask you a question. Why do we do a blood gas? Arterial blood gas measurement has been around for many decades, certainly throughout my entire career and for many decades before that. And when we do a blood gas, we get a printout that looks something like this. And I believe that there are three reasons for doing a blood gas. The first is to look at the adequacy of oxygenation and ventilation and to make adjustments either on the ventilator or with oxygen apparatus. The second is to determine whether there is a respiratory or metabolic component to their acid-base disturbance if present, and to examine the degree of compensation. The third thing to do, of course, is to look at other diagnostic tests that are concurrently performed, and there are all kinds of other things that are really useful on a blood gas. These are the hemoglobin concentration in the presence of abnormal hemoglobins like methemoglobin or carboxyhemoglobin, and there's the electrolytes, sodium, potassium, chloride and calcium. It also measures glucose and it measures lactate. A lot of stuff is measured, and I really want to point that out at the onset of this talk and of this series. Most of the information that we need these days about acid base is already in the printout. In this tutorial, I'm only going to look at this line, and that is the pH, and that is the relative level of acidity of the blood. Let's start with a scenario. You're called to the emergency room and you're told that there's a confused man there and he's very short of breath, and they took a blood gas but the machine broke and all they got in the printout was a hydrogen ion concentration of 100 nanomoles per litre. How sick is this patient? And, well, you may not be familiar with this hydrogen ion concentration thing. What does it actually mean? And how can you convert that to something that you do understand, presumably, and that's the pH. So let's start with a little bit of chemistry. We're made up principally of water, and water is made up of two gases, hydrogen and oxygen. And it looks a bit like this. There are two hydrogen ions and one oxygen, and the molecular mass is 18, made up of an atomic mass of 16 of oxygen and two 1-proton hydrogen ions. When we quantify chemicals, we use the term moles, and a mole has a complex number. It's known as Avogadro's number, but it's most easily understood as 1 gram times the molecular weight. So how many moles is there in 1,000 mils of water? The molecular mass of water is 18, as I've mentioned, and 1 mole therefore is 18 grams. If 1 kilogram is 1 litre, then 1,000 divided by 18 is 55.5 moles. So there's a lot of water in water, and I'll get back to that in a second. This is very important to understand. Do you ever wonder why there are droplets of rain, why you can swirl a glass of water, why the sea is the sea? It's because water has a high surface tension, and the reason why it has that is because it's slightly polarized. That means there is an uneven charge. There's a slight negative charge on the oxygen side and a slight positive charge on the hydrogen side. And as a consequence of this, water molecules stick to each other and clump together with electrostatic bonds. The other point that you must understand about water is that it slightly dissociates into its component parts. So theoretically, that means the H2O breaks into OH- and H+. The idea that there are free protons is a bit of a myth. Whenever you hear people talking about acid-base, they go on and on about protons or hydrogen ions as if there's a big swarm of hydrogen ions floating freely through the body fluids, being transcellularly exchanged ion for ion with, for example, sodium. But this is not correct. Let's get one thing clear. There are essentially no free hydrogen ions floating around your body fluid. None. Nada. Zippo. Basically, when we talk about hydrogen ions, or H+, we are using a shorthand expression for a glob of water with a hydrogen ion poking out. And this can have any chemical form you like, as long as there's a plus at the end of it. So you get this big lump of water, and just one part of it has an extra hydrogen ion sticking out. And here's the thing, it doesn't just stay where it is. That hydrogen ion bounces around each glob for about 200 nanoseconds, so it's all over the place. But there isn't a single proton floating around. In every mole of water, there are 2 moles of hydrogen. That means there are 111 moles of hydrogen ions as water in extracellular fluid. So there is approximately 111 times 6 times 10 to the power of 23 hydrogen ions in 1 liter of extracellular fluid, and this is a very large number. On a normal arterial blood gas, the free hydrogen ion activity is measured at 40 nanomoles per liter. Now, nanomole is 1 billionth of a mole. That's 40 times 10 to the minus 9. And the actual real concentration of free hydrogen ions is significantly lower. This is an extremely small number. In comparison with sodium, there are 140 millimoles of sodium per liter in extracellular fluid, which is 0.140 moles or 10 to the minus 3. Hydrogen ions have a concentration in the 10 to the minus 9 range. So for every 1 hydrogen ion, there are 3.5 million sodium particles. So 40 nanomoles at 37 degrees Celsius, and that is not a free hydrogen ion. There are no free hydrogen ions. It's a glob of water that has the activity as if it had a single hydrogen ion. So that H+ refers to the hydrogen ion activity, not the concentration. And what that means is that if a patient comes in vomiting and has an alkalosis, it cannot possibly be due to a whole body deficiency of hydrogen ions, because there is a limitless supply of hydrogen ions in the body. They're made up 60% of water. So let's move on and talk about what acids and what bases actually are. In ancient times, the Greeks described acids as being sour-tasting substances, and later bases were considered chemicals that balanced acids, and they were bitter-tasting. When an acid and a base were put together, salt and water was constructed, and that's why we have sodium chloride, sodium lactate, etc. I believe the modern concept of acid-base can be traced back to William Brooke O'Shaughnessy in the 1830s. He was an Irish physician working in Scotland, and he essentially worked as a forensic pathologist who dealt with the cholera epidemic that occurred in Edinburgh and Glasgow back then. And his writings are quite remarkable for the times. In fact, if you want to read a really interesting biography, read his biography. He later got involved in India and telegraphs and all kinds of stuff, but I believe he's the founding father, really, of modern intravenous fluid therapy. But how he described the blood of cholera patients was as follows. Of the free alkali contained in healthy serum, not a particle is present in some cholera cases and barely a trace in others. All the salts are deficient in blood, especially carbonate of soda. And what he's describing there is the fall in the bicarbonate level of blood in a patient with metabolic acidosis from sepsis. Early in the 20th century, it was unclear why diabetics and uremic patients seemed to go into comas and die, but it was believed that this was associated with the accumulation of various acids in the blood. And again, these were associated with a fall in the bicarbonate levels. Svante Arrhenius was a Swedish physicist who became a chemist. It was he who introduced the theory of ionization. Now, that is now an established fact, that salts separate into their component parts in liquids. He also introduced the first widely accepted theory of acid-base. It took 20 years for this theory to be accepted and another 20 for it to be widely rejected. His theory posited that in any solution based on water, that's an aqueous solution, ionized atoms or molecules could alter water dissociation and the chemical structure of water. For Arrhenius, an acid is any substance that delivers a hydrogen ion into the solution. A base is any substance that delivers a hydroxide ion into the solution. If that was the only theory of acid-base, then teaching acid-base balance would be really easy. Unfortunately, the chemistry world is not the biology world, and although this theory works perfectly well for all biological organisms, it doesn't work for all white-coated chemists working with test tubes in laboratories. And as a consequence, this was superseded by a different theory in the early 1920s by Bronsted and Lowry, who were working independently, and they proposed different definitions for acids and bases. Acids were substances from which a proton could be removed. They were proton donors, effectively, and bases were substances that bind hydrogen ions or protons. They're acceptors. This is an almost universally accepted theory. It's not a fact, it's a theory. And you learnt this in school. Hydroxyl, which produces significantly greater chemical equivalence to extracellular acid-base reactions, was cast aside. And it's been forgotten by pretty much everyone. So this led to the era of the all-conquering hydrogen ion, the confusion of acids versus conjugate bases, and the incomprehensibility of acid-base for most clinicians. Now, I want to point out that the Arrhenius theory and the Bronsted-Lowry theory are actually quite compatible with one another, and you just have to kind of think a little bit outside the box. Key to understanding acid-base in biology is that water is amphiprotic. It can act as an acid or a base. For example, if hydrochloric acid is dissolved in water, it ionizes to produce hydronium and chloride. HCl, hydrochloric acid, is a Bronsted-Lowry acid. It is the proton donor, and water is the proton acceptor. Functionally, however, when you measure the chloride ion, you know there must be an associated hydrogen ion in the system. Chloride represents the presence of an acid. According to Arrhenius, chloride is the acid and it delivers hydrogen to water. On the other hand, mixing sodium hydroxide in water results in the release of a sodium atom and a hydroxylized water clump. In this situation, sodium hydroxide is a Bronsted-Lowry base as water donates the proton to sodium hydroxide. The presence of sodium is indicative of base, and sodium is an Arrhenius base. Regardless of your approach, I want you to think of chloride as hydrochloric acid and sodium as sodium hydroxide. This will make acid-base balance easy for you. Let's move on to the pH scale. Everybody is familiar with the use of the pH scale for measuring relative acidity, and it was originally developed at the Carlsberg Brewery in Copenhagen in 1909 by Søren Sørensen, a chemist working at that laboratory at Carlsberg. He noticed that the relative acidity and alkalinity of a liquid significantly impacted its taste, and nobody wants to drink sour beer. As directly measuring the hydrogen ion concentration wasn't really possible back then, he developed an elegant electrode to measure the hydrogen ion activity, and then he reported it in a simple manner, the negative logarithm of the base 10 of the hydrogen ion activity, and he called that the pH. The higher the pH, the lower the hydrogen ion activity, and the lower the pH, the higher the hydrogen ion activity. Thus, the hydrogen ion, historically but not necessarily accurately, became key to defining the level of acidity of solutions. That pH is the negative log to the base 10 of the hydrogen ion activity, and that's a small number because the self-ionization constant of water is 10 to the minus 14. So there is essentially 10 to the minus 7 hydrogen ions and 10 to the minus 7 hydroxyl ions. That's neutral pH. And at neutral pH, the number of protons is exactly equal to the number of hydroxide ions. And that neutral pH is 7 at 25 degrees Celsius. So neutral is hydrogen equals hydroxyl. To be an acid, there needs to be more hydrogen ion activity than hydroxyl ion activity. And to be a base, there needs to be more hydroxyl ion activity than hydrogen ion activity. Over the next number of decades after Sørensen developed the pH idea, there were various different machines devised to measure pH, and it wasn't really until the 1950s that blood gas machines as we understand them became available for clinical practice. And the modern radiometer machine that was developed way back in the 1950s has 3 electrodes: a pH electrode, a carbon dioxide electrode, and an oxygen or Clark electrode. This is the original blood gas machine developed by Severinghaus and colleagues. Let's look at the hydrogen electrode. The first component of the hydrogen electrode, or the pH meter, is a voltage meter that measures changes in electrical charge. To this is connected 2 electrodes. The first is a pH sensing glass electrode, and the other is a pH independent reference electrode. Both electrodes are connected to the voltmeter. The reference electrode is in a potassium chloride solution that does not contact the blood. It is a salt bridge. The pH electrode is located in a thin layer of silica glass and surrounded by a chloride-based buffer solution. The other component of this system is the sample container into which blood will be injected. The difference in the charge between the 2 electrodes, which are essentially in similar chloride baths, will reflect the amount of hydrogen ion activity in the blood. So let's see what happens. So blood is injected into the sample chamber. This blood will have a different hydrogen ion activity than the buffer solution, and I'm just going to refer to these as hydrogen ions, but it's really a glob of water with hydrogen ion attached. The hydrogen ions interact with the outer surface of the glass, and this causes hydrogen ions to be formed within the chloride solution on the inside of the glass. This changes the voltage within that, and it causes a generation of voltage that goes to the pH meter, and that the difference in the voltage between the control electrode and the measurement electrode is a reflection of the hydrogen ion activity, which is converted into pH. If you look at the body, the extracellular fluid has a pH of 7.4, and that works out at hydrogen ion activity of 40 nanomoles per litre. Is it possible that iced tea and hot tea have different pHs? Absolutely they do. If you heat water molecules, they dissociate more. And so you get an increase in the hydrogen ion activity and the hydroxyl ion activity, and the pH as you measure it will fall. But despite the fall in the pH, the solution remains chemically neutral because there's still an equal amount of hydrogen and hydroxyl. Similarly, if you cool water molecules, they dissociate less, so there's less hydrogen and less hydroxyl, and because you only measure hydrogen with a pH meter, the pH goes up, but the solution remains chemically neutral. And it's important to understand this. The warmer the solution, the greater the number of hydrogen ions that you could measure, but there's also the same number of hydroxyl ions that you're not measuring. So even though the pH appears to fall, the tea that is heated up to 100 degrees doesn't immediately start rotting your teeth because it's a neutral solution. Body fluids can only become more acidic if the hydrogen ion activity is greater than the hydroxyl ion activity. That is, hydrogen ions greater than hydroxyl. Body fluids can only become more alkaline if the hydrogen ion activity is lower than the hydroxyl ion activity, and that is hydrogen less than hydroxyl. If hydrogen equals hydroxyl, the solution is neutral. Also, and importantly, for those of us who work in clinical medicine, the pH is only of value if it's referenced to the standard temperature of 37 degrees, because outside of that range, it is really misleading. As a rule of thumb, the pH of blood falls by 0.015 units for every 1 degree Celsius rise in temperature. So for example, we have Steve who's in the ICU with sepsis. His temperature is 40 degrees Celsius. What should his pH be? 7.4, 7.35, 7.45, or 7.55? Well, there can only be one correct answer here, and it's 7.35 because his blood is warmer than normal. Normal blood temperature is about 37.5 degrees. So his temperature is increased by about 3 degrees Celsius. Starting pH is 7.4, 0.015 times 3 equals 0.045. 7.4 minus 0.045 equals 7.355. What about Brian, who's in the ICU with hypothermia? His temperature is 32 degrees Celsius. What should his blood pH be? 7.4, 7.35, 7.47, or 7.57? You can pause this and work it out. The correct answer is 7.47. His temperature has decreased by 5 degrees Celsius. Starting pH is 7.4, 0.015 times 5 is 0.075. 7.4 plus 0.075 equals 7.475. The blood is more alkaline at a lower temperature. The Kw dash is the water dissociation constant, and it looks at how water dissociates. At 25 degrees Celsius, the Kw is 1 times 10 to the minus 14. The pH is 7, and we call that neutral. As blood becomes cooler, it is less dissociated. As it becomes warmer, it becomes more dissociated. But I want you to look at the numbers beyond 25 to 30 to 40. Notice the way the pH drops. At 40 degrees, the pH of water is 6.77. And that's really interesting because at 37 degrees, the intracellular pH is 6.8, which is chemically neutral. So let's get back to the picture I showed you a minute ago. The extracellular pH is 7.4. The intracellular pH is 6.8 at 37 degrees Celsius. And that means that intracellular pH is chemically neutral at 37 degrees Celsius. The hydrogen equals the hydroxyl. The extracellular pH is chemically alkaline at 37 degrees Celsius. There is more hydroxyl than there is hydrogen. Now I want to show you a rule of thumb for how you can calculate the hydrogen ion activity versus the pH. For a 1 nanomole per liter increase in the hydrogen ion activity, that results in a 0.01 fall in the pH. let's go back to our ED patient who had a hydrogen ion activity of 100 nanomoles per liter. His hydrogen ion activity has increased from 40 to 100 nanomoles per liter. That's a 60 nanomole per liter increase. By using the metric of 1 equals nanomole results in a fall of 0.01 fall in pH, then the pH will have fallen by 0.6 from 7.4. So his pH, that ED patient's pH, is 6.8. That is quite acidic, and this patient is in significant trouble. I'll just show you a little table of hydrogen ion activity versus pH. And be aware, between 7.4 and 7, there is a doubling of the hydrogen ion activity. Let's move on to acidosis and alkalosis. Now, please don't be a boring bench chemist. These terms are parochial to medicine, and they were agreed by multiple consensus conferences in the 1960s. Everybody agrees that a normal pH of arterial blood is 7.4. Most people agree that an acidosis occurs somewhere below 7.4, usually below 7.35. However, due to buffering and compensation, the pH may be higher than this with acidosis. So to define acidosis, in my view, I think this is reasonable. Acidosis is a pH of less than 7.35 or a pH of less than 7.4 with a bicarbonate that's less than 24 millimoles or milliequivalents per liter and a PaCO2 that's lower than 40 millimeters of mercury or 5.3 kilopascals. In and of itself, acidosis is not terribly harmful if the pH is greater than 7. However, this should be interpreted as a marker for significant underlying disease if the patient is in the resting state. Obviously, if the patient has just run a marathon, their pH is going to be low from all the lactate that they have generated. Nevertheless, once the pH goes below 7, the extracellular fluid or blood pH starts approaching that of intracellular fluid, and problems with transcellular ion pumps become apparent. Often this manifests with hyperkalemia. You start seeing cardiac arrhythmias, and that can lead to a cardiac arrest, and that's why people die of diabetic ketoacidosis. They have a cardiac arrest from hyperkalemia. The stroke volume falls. There is widespread vasodilatation, and catecholamines become less effective. Most enzymatic systems in the body become malfunctional below a pH of 7, and the body goes to an enormous effort to try and keep that pH up there in the normal range. An alkalosis is a pH in excess of 7.45. It is usually not a marker of acute critical illness. You can certainly see it in some limited circumstances that I will visit later in this course, but rarely do patients actually come in acutely critically ill with alkalosis. Maybe 2 or 3 in 100 patients that we see in our clinical practice. It may be caused by hyperventilation or relative hyperventilation, and it may manifest iatrogenic complications of critical illness. For example, dehydration due to diuretics or hypoalbuminemia. It's not infrequently caused by severe vomiting where patients develop acute hypochloremia. The major manifestation acutely is widespread vasoconstriction and generalized malaise. The major issue you must be aware of with alkalosis is it may mask the presence of a malignant acidosis consequent of systemic disease. In this situation, we have an acidifying process, for example, acute kidney injury. The pH should be somewhere in the region of 7.1, but due to direct compensations such as hyperventilation or concomitant alkalosis due to hypoalbuminemia or extracellular fluid deficit manifest by hypernatremia, that acidosis may be buried inside this alkalinizing process, and the pH may be artificially higher than you would expect. And this is one of the major problems with the old-fashioned approaches to acid-base. You may not see the problem because you have multiple problems going on, some relatively benign, but something very malignant may be lurking in the background. I need to mention the conventional terminology for acid-base disturbances that was agreed at a series of consensus conferences in the 1960s, and whether you like them or not, they are universally accepted, and I'm going to use them in this series. First of all, acidosis. If it's caused by a rise in the partial pressure of carbon dioxide on its own, we call this respiratory acidosis. The pH falls as a consequence of the high PaCO2, and this may be acute or chronic. If there is an increase in the amount of organic or mineral acids in the blood without an increase in the concomitant quantity of mineral bases, or even a reduction in the quantity of mineral bases, or independently a reduction in the quantity of mineral bases, we call this metabolic acidosis. If the pH is greater than 7.5 and the PaCO2 is low, the patient has respiratory alkalosis. This may be acute or chronic, primary or secondary. If there is an increase in mineral base activity and or a reduction in mineral acid activity, then we call this a metabolic alkalosis. Metabolic alkalosis may also occur due to a reduction in serum albumin. Albumin has a negative charge, and it can be reduced in critical illness due to hepatic reprioritization towards globulins and other proteins, or when you give lots of IV fluid to the patient, you hemodilute the patient and the albumin level falls relative to the other electrolytes. The other term that is widely used in the understanding of acid-base balance is the concept of compensation. So, for example, a patient may have an increase in the amount of organic or mineral acids. By organic acid, I mean, for example, keto acids or lactate, and mineral acids, we're thinking about chloride. Or they may have a reduction in the mineral bases. They may be hyponatremic. The pH will fall, and for example, the pH may fall to 7.1, and we call this acute metabolic acidosis. Two things happen. One of them is that the bicarbonate falls, but the patient also starts to hyperventilate to blow off carbon dioxide because carbon dioxide is an acid. So the PaCO2 drops, and we call this a secondary respiratory alkalosis. Most people refer to this as compensation. And as a consequence of this, the pH rises back up closer to the 7.4 region. It will never get to 7.4, and if it goes above, there's a concomitant metabolic alkalosis. I want to finish this tutorial with a very useful rule of thumb. I call this the rule of 40. The physiologic extracellular pH is 7.40, so 7.40. At that level, the hydrogen ion activity is 40 nanomoles or 40 nano equivalents per liter, and the PaCO2 in millimeters of mercury is 40. So you have three separate 40s. And if any of these become misaligned, there is an acid-base abnormality going on. So try and keep this in the back of your head. I'm afraid there's no easy kilopascal version of this, but if you're a person who uses millimeters of mercury, this is quite helpful. Now let's review this tutorial. In this tutorial, I discussed hydrogen ions and the definitions of acids and bases. I discussed the pH scale and how it relates to hydrogen ion activity. I talked about the concept of neutrality, the impact of temperature on pH, the terminology for acidosis and alkalosis, respiratory and metabolic. Next time, we're going to delve into acid-base chemistry, and I'm going to talk about carbon dioxide chemistry and production, acute respiratory acidosis, chronic respiratory acidosis, and acute respiratory alkalosis. Join me then, and I guarantee you'll learn something. So that was the power of hydrogen. Next time we're going to look at the role that carbon dioxide plays in acid-base balance. If you're enjoying these tutorials, don't forget to subscribe or follow me at ccmtutorials.org.